number 9. Number 9 has a set with 5 vectors. Those vectors are in R4. We want to know, part A says, does S vector, the set S, does it span R4? And then part B, is S a basis for R4? Well, I'll tell you what, it's easy to answer part B from something that we learned before that says that talks about dimension, right? Dimension is the number of vectors in the bases. Okay, we know that the dimension of R4 is 4, right? So that therefore a basis for R4 needs to have only 4 vectors. But look at S. S has 5 vectors. So the answer for B is already no, okay? So you can use that argument, and it's from theorem, let's see here. Well, it's from the definition of dimension, okay? So you can use theorem 4.11, that's on page 226. It says, if a vector space has one basis with n vectors, then every basis for V has n vectors. So we know that for R4, so let's go ahead and answer in part B, okay? In this case, it's easy. We can use a basis for R4 is, you know, the standard basis. They call it canonical basis. Anyway, 1 0 0 0 1 0 0 0 0 1. It doesn't matter the order, but if I do 0 0 1 0 and 0 0 0 1 is a basis for R4. Any vector in R4 can be written as a linear combination of these 4. Actually, this is a very good exercise. So let me go ahead and do that here. So if you pick a vector in R4, right? So let's say A, B, C, D. How do you write A, B, C, D as a linear combination of these 4? Very easy. A times the first vector, B times the second vector, C times the third, and D times the fourth. That's your linear combination right there. Okay? See, there it is. So, and these are certainly linearly independent, right? If you put 0, 0, 0, 0 here and try to write a linear combination, you put C1, C2, C3, C4, I mean, that's just the identity matrix, right, with the right-hand side being zeros. So you're going to find C1 equals to 0, C2 equals to 0, and so on. So this is a basis, okay? The canonical basis, or the standard basis, is always, I mean, the standard set like this is always linearly independent. Okay, the dimension, that means dimension of R4 is 4. So any basis for R4 has 4 vectors. Okay? But S, the set S here, on number 9, has 5 vectors. So S cannot be a basis. For R4. So that's the answer for B. Okay, let's go back to, now let's go to A and answer A. A says, does S span R4? Well, it could span R4. So how do we know? Well, we pick a vector. Pick a vector in R4. Let's say A, B, CD, okay? And see if you can write that vector as a linear combination of those 5 vectors there. So, okay, there it is. We want to write any vector in R4. So pick a general vector and see if you can write as a linear combination of those 5 vectors. So if you set up the system, okay, let's do that. Okay. So that will be the system that you would need to solve, maybe by hand. Calculator you can't. But there is an easier way, because we know what R4 is. R4 is the 4th dimension of space, and we do have a basis, a standard basis. See, the 1, 0, 0, 0, 1, 0, 0. So that's the basis. So I could, instead of picking A, B, C, D, let's see if I can solve the system for all those 4 vectors here from the standard basis, okay? So if I can write each of the vector in the basis, of the vectors in the basis, as a linear combination of those 5, that means this vector here can also be written as a linear combination. Okay. So you can test, so check So let me write that here. Okay. Here you can check only these 4, right? You don't have to check. I mean, picking a vector in R4, there are millions or infinite number of vectors. Excuse me. But if you check only the vectors in the basis, then that will be enough. Okay, so let's do that for each one of them. So put in the calculator, the right hand side here, put 1, 0, 0, 0, and see if you can solve it. And then if you can, then try the second one, see if you can solve it. If you can solve it for all of them, then there is a solution for this system here, for this equation here. And therefore, those vectors, these 5 vectors here will span R4. So let's do that. Okay, I put this matrix, my matrix A is, it's a 4 by 6 matrix, okay? But I didn't put A, B, C, D in there. I put this first vector, 1, 0, 0, 0 here, okay? That's my first matrix. And I reduce it, and this is what I got. So look at this. So look at the last row. Last row saying it's 0 equals to 1, right? See, this is an augmented system. It will be 0 equals to 1. That's impossible. So at this point we can stop here because it already failed for this one, right? So this vector here cannot be written as a linear combination of those 5. So that already fails. So we can say 1, 0, 0, 0 is not in the span of S, right? S is those 5 vectors. So S cannot span R4. Okay? So let me summarize the idea here, okay? We want to show that the set S here, let me point that here for you. We want to show that the set S spans R4. How do we do that? In general, this is what we need to do. We pick a vector, a general vector in R4, A, B, C, D, right? And we try to write that vector as a linear combination of those 5 vectors in S, okay? Then you set up the system, and this is pretty tough to do it by hand, okay? And you can do it in the calculator because you don't know what A, B, C, D, and are. But you know what a basis for R4 is. It's the standard basis. You can do that with any basis, but here we have an easy one. It's the standard basis. So all I have to do then, because that basis generates the whole space, the whole R4, all you have to do is to check each one of them, right? So check 1000, put it here and see if you can solve it. If you can, you're not showing that it's the span of S is R4, but you're showing that this vector here is in the span of S. Okay. Then do the same for the second one. If all of those 4 vectors here are in the span of S, in other words, if all those vectors here you were able to find a linear combination, you can solve for those C's, then the span of those vectors should be in the span of S. The span of those vectors is R4 because those 4 vectors is R4. Okay, so that's another way of doing it. Okay, so the conclusion is S cannot span R4.